I think a common complaint about the many worlds interpretation is that it adds so much to quantum theory. You might have heard that there are like these infinite number of worlds, and that just seems really excessive. But I'm going to try and explain in this video why, mathematically, actually the many worlds interpretation is a simplification of quantum theory. It takes quantum theory that has itself some really nasty mathematical properties. In particular, there's two rules of quantum mechanics that literally contradict each other. They can't both mathematically be true. It takes one of those rules and just deletes it. So it takes what's called the measurement collapse rule, that measurements cause superpositions to collapse, and just deletes that rule. And that's it. That is the many worlds interpretation of quantum mechanics. I'm going to explain why that is still possible, why just deleting a part of quantum theory would still give you basically the same results. It took the example that I'm about to show you to convince me that that really is the case, and that the many worlds interpretation, I think, is the best interpretation of quantum mechanics because it's so simple. So we're going to start by talking about what exactly the problem in standard quantum mechanics is. So this is called the measurement problem. Here are the rules of standard quantum mechanics. So the first one is quantum states are vectors. That probably doesn't mean a whole lot to you, so I'm going to show you an example that will help explain what that means. So suppose I have an electron. Electrons have this special magnetic property called spin, and what it does is it determines how the electron is going to behave in the presence of a magnetic field. So there are these machines called Stern-Gerlach machines. They're basically machines that make a non-uniform magnetic field so that the electron has sort of two choices. It can either go upwards or it can go downwards. Now I'm going to talk about the state of that electron before it goes into the machine. So it could be in a state that we'll call spin up. This is just some funny notation to talk about the state of a quantum thing. Don't worry too much if it looks scary. But okay, if it's in state up, what that means is it will go up. So an electron that was in up will go up. On the other hand, if the state had instead been down, then yep, predictably it would have gone down. But here's the weird thing about vectors. You can have combinations of them. The state of this electron could have been a combination of up and down the whole time. Now, if that was the case, what happens to the electron? Quantum theory would say that, well, because it was in both of those states, it needs to go both ways. It needs to go up and down, which is very weird, but that is the first rule of quantum mechanics. By the way, I've left off some factors that you may or may not know should go in there. I'm going to leave them off for this whole video because I don't think that it changes the analysis much in this example, but just so you're aware, they're supposed to be in there. Let's look at the second rule. I would call this the Schrödinger equation. The Schrödinger equation is just basically a rule for telling you how the state of an electron will evolve over time. So it says, if I put this electron into a certain magnetic field, or if I did something else to it, what's going to happen to its state? It has to change, but how is it going to change? So that's all the Schrödinger equation is. Then we have the final rule, and that is the problematic one. It's this. Measurements cause collapse. So for example, suppose that I had put in a little detector here and here. So what these detectors do is if this detector sees an electron in the bottom path, it will alert this machine and then the machine will point to down. But if the machine sees the electron at the top path, then the machine will point to up. So it's just a measuring device that is going to measure whether the electron is up or down. What do you think would happen if we put in an electron that is a combination of up and down and we measured it? Well, the sensible thing to assume is that you would see both. Somehow there would be like sort of two arrows and it would point to both up and down. But that isn't what happens. In fact, this rule says that the measurement causes the state to collapse from this superposition to just one. And which one? It's going to be random. So in this case, it'll be 50-50 odds. So let's just say that it happens to collapse to being just down. That means that this machine will measure it being in the down state. And from now on, now that it's measured it, the state is down and remains down. So why is this measurement rule so bad? I mean, the other two seemed weird enough themselves, right? But the reason why the Schrödinger equation and the measurement rule can't coexist is because they mathematically contradict each other. So in the Schrödinger equation, everything is evolving in time in a way that doesn't lose any information about the previous state. So if you look at the state now, you would be able to tell what the state was just before. That isn't the case at all if you have measurement collapse. Once the state collapses, you have no idea exactly what kind of state it was before that. So there's this abrupt change in the state of the system, which, yeah, the Schrödinger equation doesn't allow. Another reason why that's so weird is because both of these rules apply to, quantum objects. And so you might think, okay, quantum objects are just like atoms and things, right? But what is inside of this measuring device if not just a bunch of atoms? So why is it that this measuring device, despite just being a physical object, just despite being made of regular stuff like anything else, obeys completely different rules to the rest of quantum mechanics? And what's the arbitrary line? Like, what counts as a measurement? Does it have to be very, very big? Well, Bohr certainly thought so. He imagined that there was a certain line where the classical world starts and where the quantum world stops. But exactly how big is that? Does it have to have 10 to the 23 atoms and then it's classical, or below that it's quantum? I think that's kind of ridiculous. Why should there be an arbitrary line in the sand where this rule starts applying and this rule stops applying? In any case, quantum theory doesn't give a precise definition of measurement, so you never even know when you're allowed to be using this idea of a measurement or not. So, this is the measurement problem. This is what Many Worlds is trying to fix. I already alluded to it, but the way that Many Worlds tries to solve this is by just removing that rule altogether. Some of you might have watched some of my videos that I made on Bohmian mechanics, and you might be thinking, yeah, well, Bohmian mechanics also solves the measurement problem. It does, and in a sort of similar way. So it also removes this measurement causes collapse rule, but then it has to add a few extra rules, so some equations for how the state of the objects are governed by the Schrödinger equation. And yeah, it's a little bit of extra structure on top of regular quantum mechanics. So I still really like it. I think that it is a very cool demonstration of how you can get the same results, but with slightly different maths. What I really love about the Many Worlds interpretation is that it's not adding any extra structure on quantum mechanics at all. It actually just removes this rule, and that is it. But surely that's not going to work out. I mean, if you just remove this rule, then what would happen here? You would have had this state starting like this, and then since there's no measurement to collapse it, wouldn't that mean that when you do the measurement, you see both of those options happening? But we know that that isn't what happens when we do measurements in the lab. So surely this is wrong. Surely this can't be enough to get the same results as all the ones we're used to from quantum mechanics. All right, in a moment, I'm going to go through this example again, and we're going to see how it is enough to actually remove this statement and still get all of the predictions that we would have made with regular quantum mechanics. Before we get to the Many Worlds interpretation though, I want us to go back to regular old quantum theory and figure out what measurements really are. So in quantum theory, it's not exactly well defined whether something counts as a measurement or it doesn't. So I think it makes sense for us to go back to regular quantum theory and understand measurements a little bit more, because then we have a better chance of being able to get rid of them entirely. Let's see if we can come up with a very clear-cut experiment that we can do that tells us whether the measuring device that we're using really is a measurement or isn't. All right, so this is the experiment that I propose we do to be able to tell whether something's a measurement. First, we have a Stern-Gerlach machine just like before, and so that causes an electron that's in the up state to go up, down state to go down, as before. But now I've got another Stern-Gerlach machine that I've just flipped upside down. And what that means is the magnetic fields are all reversed, so everything goes back as it was before. So electrons that were in state up go back to the center, and so do ones that were in down. And so this by itself is like nothing happened. So if I have a quantum state, let's say this, when it goes through here, it changes, but then it changes back to what it was. And so it comes out exactly the same as before. So for example, if I had an electron that was in the up state, it goes up, then it goes back to the center, and it still stays in that up state. Now, this is the extra bit that actually does something, and it's another Stern-Gerlach machine that I've taken and just flipped onto its side. And so what it does is it has a magnetic field in the sort of left-right direction, so it splits electrons that way. What is going to happen to our electron that is in the up state? It went along this path, and now what's it going to do when it goes to here? Well, for this we're going to need a few little facts from quantum mechanics, and I'm going to write them down, but I don't want to freak you out. If you haven't seen them before, don't worry about it. I'm going to tell you what they are, and all I want is for you to get the gist of this experiment. You don't need to necessarily get every one of the details. So here's the first little fact. All right, so what this says is that up is equal to right plus left. That should seem weird to you because it is, but this is just a standard fact from quantum mechanics. How it applies here is that, okay, well, there's this up thing, it's still up when it gets to here, and then we can stop thinking about the electron in terms of up and down, and instead think about it in terms of right and left. By the way, there are some coefficients that I've left off here and here, but they're not important because they're both equally big. So that means that because this thing that is in the up state is in an equal amount left and right, there's an equal probability, so 50-50, that the electron ends up here, and 50-50 that it ends up here. So if I do a measurement here, right and left, then there's a 50-50 chance that it will point to either one of these. Let's just say for now that it happens to point to the left one. So that means that you found the electron in the left state, but it could have gone either way. Now, a very similar analysis applies for if the electron had instead started off in the down state. Nothing would have happened to it here, so it's still in the down state. By the way, you're probably wondering why there's this whole thing here that just does nothing. We'll get to that in a second because we're going to add something in the middle that changes the setup. So, okay, if this was in the down state, it's still in the down here. We're going to use this fact from quantum mechanics. This is equal to right minus left. Again, that should strike you as weird. It is weird. I'm not going to explain it, but let's see what the consequence is. So this thing, if we start thinking about it in terms of up and down, start thinking about it in terms of right and left, is now equally in the right state and the left state. And so just the same as before, it could equally well turn up in either of those spots. And so when you do the detector, it'll show one of them with 50-50 probability. Let's say again that it ends up being left. Okay, interesting. Now let's see what would have happened if instead we had started off with the equal superposition, up and down. All right, again, nothing happens to it, so it's still this. Okay, good. But now, is it going to go to both sides equally? Seems like it should. I mean, like this part of it does and this part of it does. So surely the combination of them is equally likely to be left and right. But that is not correct because we can add these two together according to this rule and see what we get. All right, so let's figure out what this combination is by adding those two equations. So it seems like there should be two rights because those two rights add up together. Actually, there's just one because I've missed off a bunch of factors like I told you before, and if you took all of those into account, it would actually just only be one. So that's right. But then what happens to the lefts? Well, they cancel each other out, right? One of them is positive, one's negative. And so you get this bizarre result that the equal superposition of up and down is equal to right. Okay, Again, this is standard quantum mechanics, but it is a weird result. This is what we refer to as interference, because it's like you add these two things where you know what the individual behavior of both of them is, but the combined superposition behavior is not that, right? It's not 50-50, it's actually just 100% going to go right. And so let's see, when you put this through the machine, comes out here, this is right, and so the result is going to point to the right for sure. Good. So this has given us a way of verifying whether the state is a superposition state or not. But that wasn't our question originally. Our question was, when does something count as a measurement? So here's what I'm going to do. I'm now actually going to put something in between here. So something happens here. There could be a range of things that happen. It could just be a regular old measurement device that measures whether it was up or down. It could be a regular measurement device where for some reason you just can't see the screen and it's out of view. Or it could be that someone else has done that measurement and then they ran off with the result and they didn't tell you. Either way, you don't know what the result of the measurement is. You don't even know if it really counts as a measurement. For example, maybe someone tells you, I did a measurement, but how do you know that they're not lying? Well, this is an experiment that we can do that will let us verify whether a measurement really happened at this point or not. Here's how it goes. Suppose that a measurement did happen, right? So now the state goes from being in this equal superposition to being one of them, because we know that measurements cause collapse. We don't know exactly which result it was. It could be either up or down with 50-50 probability. Let's just say it's up, but it doesn't matter. If it was up, now, at this point, the state is up. And if you do this measurement, well, we know that up is an equal probability of left and right, so you could get either of these. Suppose we actually did get left. On the other hand, if no measurement happened, there's nothing that happened here, so this whole thing is nothing, and the state is the same afterwards. And we know that this superposition state is the sum of these, so it's just going to go right. So this setup lets you decide whether a measurement really did or didn't happen at this point. Because if you had a bunch of electrons that started off in this state, and there was no measurement here, they're still in that state, and they're all going to go to the right. But if you started in this state and a measurement happened, then 50% of them are going to go right and 50% are going to go left. If you didn't get every single detail of that setup, don't worry about it. The point is that now we have a way of telling whether a measurement really happened or it didn't happen. And so now we can go and do this experiment. And actually this experiment, or very similar to this experiment, has been done. And so let's see what does and doesn't count as a measurement. The result is lots of things count as a measurement. For example, if a measurement was done but you just didn't see the result, that doesn't matter. Even if no one saw the result. I think this is an interesting one because a lot of people have this misconception that a measurement is only a measurement if a conscious observer looked at it. But that isn't true. A machine by itself can do a measurement, and this is a way to verify it because the interference goes away if you did do that measurement. Something that obviously doesn't count as a measurement is if that measurement device is off. Yeah, clearly it can't be doing anything. But there's still a question here. It's like, how big does the measurement device have to be able to count? How many atoms need to be inside? Is it only going to be a measurement if tons of atoms in there? Or is it okay to just have a very, very small measurement device? That's going to be our next thought experiment. I'll give you the takeaway of this experiment before we even do it. We're going to use just one particle as our sort of detector. In the standard interpretation of quantum mechanics, a single particle absolutely cannot cause measurement collapse. We know that because if it did, then we wouldn't get all kinds of states in quantum mechanics that we need. These are called entangled states, and like, for example, the whole theory of quantum computers relies on entangled states being able to exist, and we have made entangled states in the lab. So we know that a single particle cannot be causing any sort of measurement collapse. But in this example, we're going to show how a single particle can, for all intents and purposes, make it look like the state of the electron has collapsed. How is that possible when I've just said that it didn't collapse? Well, the thing is that if you lose track of that particle, the one that was sort of doing the measuring, if you lose track of that measurement particle, then basically there is no way for you to tell anymore that the electron is in a superposition, even though it is. Even though the electron is still in a superposition and no collapse has happened, because you lost track of the measurement device, it looks as if the measurement is done and it collapsed. Pretty cool. All right, here's how it goes. So the particle that we're going to talk about is going to go in here. What this means is the electron, if it's in a superposition, will go both up and down. Since this particle is in the way of the down path, it's going to interact with anything that is in the down state. So if an electron comes by in the down state, its state is going to change. I'm just going to say that it has two states. We'll call them U. So it starts off in U, but then if it interacts with an electron coming in the down state, that will go to D, right? So it has these two states. What happens if an electron is in a superposition? The way to think about something like this in quantum mechanics is to think about each part separately and then to add them together. So let's think about the part where the electron is in the up state. What happens then? Well, this particle starts off as a U, so I'm just going to write it next to it. And the electron, nothing happens to it, it just flies by. It's going this way. And in this case, nothing happens to our particle either. It just stays in the U state because it didn't interact with anything. On the other hand, if the electron had been in the down state, sure, this particle would have started off as a U, but something would happen to it. So the electron would still fly by without a care in the world, but now our particle would end up being in the D state. And like I said, if we want to deal with the superposition, so that's up plus down, put some brackets around that so we don't get confused. This is the case where we have up plus down, but this other sort of measuring particle starts in the state U. That's what I've written down here. Again, don't worry if the notation looks very strange. It is. What happens to this? Well, it's the sum of what happened to the other two. And so I'm going to write those out. So for the up bit, it's this. And for the down bit, it's this. Some of you might recognize this as a maximally entangled state or a Bell state. These two particles have become entangled. You can't talk about what this particle is doing without also referencing what this particle is doing as well. But you can see that this state is a quantum superposition. You know, it has this plus in it, so it means that it's doing really both of those things. So in the same way the electron is now going through both of these paths, this thing is in the state of both having detected the electron and having not detected the electron. So this, like you can see, is essentially a measurement. If I could just take away this particle and then measure it to see whether it's in the U state or the D state, it would also tell me whether the electron is in the up state or the down state. But we're not going to do that. We're going to let this little particle go off wherever it wants and forget about it. We've just got our electron. What do you think is going to happen when we put it through the rest of this experiment? Is it going to act as if it's been measured, or is it going to act as if it's not been measured? There's kind of arguments that you could make for both possibilities. For one, this hasn't been measured. We know that. We know that this was not technically a measurement. The state is not collapsed. The electron is still in a superposition of doing both of these things. But on the other hand, this really does look like a measurement in a lot of ways. So what's going to happen? Let's let the maths figure it out. So the way to do this kind of maths is like we did before, we stop thinking about the up and down states, and instead we start thinking about the left and right states. So we're going to take these equations and sub them into here. So I'll just go ahead and do that. Okay, I just rewrote this state up here so I have a little bit more room. But by the way, you might think it's kind of weird that we have to keep talking about what the red particle is doing, even though it's now long gone. You know, it's flown off. So why is it that we have to keep talking about it when we're talking about the state of the electron? Unfortunately, we're forced to, because the maths of entanglement means that you literally just cannot write the state of this electron without talking about the red particle anymore. So we're going to have to just keep that there. Okay, so all I've done here is that I've taken the up and used this rule, put it into here, taken the down and converted it using that rule, put it into here. I totally understand if you're like, well, what is this mumbo jumbo? What are all these crazy arrows everywhere? Look, don't worry about it too much. But the point is that we're kind of going from thinking about everything in the up-down basis to the left and right basis, because that is going to tell us what is going to happen when we do this measurement. You might remember that's exactly what we did before when, you know, in the other case where there was no red particle, there's nothing there. We had this, and then we had rewritten it by sort of substituting in both of those things as this plus this plus that minus that. I'm going through that very fast, but if you remember, this is why we figured out that if there was nothing happening here, if nothing had happened here at all, then this state would have just gone to the right, because this and this cancelled, and you ended up with just the right component. Is that what's going to happen here? Is this thing going to go right? Let's see. All right, what happened here? This is just how we do expansion. It's not too different from how you're probably used to, but this bit and this bit become that bit and that bit become that. If we take a step back from the mathematics though, what this is saying is actually very interesting. It's saying that this state that's here, before it goes into this machine, is a very interesting superposition of a bunch of things. It's a superposition of this particle being in a state up, in other words, it detected nothing, and the electron being left and right, so that's those two states, and a superposition of that plus this particle having detected something, and this electron being in a superposition of to the right and minus to the left. Okay, so it's great that this minus is still there, because it looks like it should be able to cancel in the same way that these minuses left. But are we able to do it? We want this to cancel with this. Do you see the problem? Like, sure, these terms look kind of similar, but they're not the same. This one has a U here, and this one has a D. And so, in other words, they can't cancel. There's nothing that you can do extra to simplify this state. Well, what does that mean then for this experiment? Is this particle interaction going to count as a measurement, in which case it's going to go 50-50 either way? Or is it not going to count as a measurement, in which case it will 100% go to the right? So the way to do this is to just count up the weight of the terms that are going to the right and the weight of the terms that are going to the left. And as you can see, they're equal. And so there's a 50-50 chance of the electron going either way. And that means that someone who is doing this experiment will decide a measurement must have happened. Let me just reiterate how weird that is. So it looks to a person who's trying to verify whether a measurement did or didn't happen that a measurement happened. But we know by looking at this maths that no measurement happened. A measurement in quantum mechanics is a collapse. The state has to break down. That's not what happened. Every part of the state is still there. The up component is still there. The down component is still there. But for every way that you can try and verify that a measurement did or didn't happen, it will look like the measurement happened. So what's going on? The thing that's going on is that that extra particle, that red particle, is taking away a bunch of information about this electron with it. And whenever that happens, now it will look to anyone else who doesn't have access to that red particle like the electron has collapsed. that doesn't mean that it really has. And the way that you would be able to verify that it really hasn't is by somehow going back and tracking down this red particle, bringing it into another experiment where both of these particles are present and measuring both of them. So you could do what's called a Bell measurement, for example, and you'd be able to tell that these are in a non-collapse state. But if you don't have access to that red particle, you have no way of telling that in fact the electron is not in a collapsed state. And so that is kind of how Many Worlds works. Many Worlds says that measurements, real measurements, the type that quantum mechanics goes on about, don't happen. There are no collapses. Instead, there are interactions, like this interaction with this red particle. And whenever an interaction happens, a few atoms interact, one of them just flies off, could be a photon going away at the speed of light. If you don't have access to that particle, then to you, it will look as if collapse happened. And so you don't really need collapse to be there at all. I think this is a super beautiful solution to the quantum measurement problem. And by the way, I've only shown it to you for this very simple example, but you can mathematically prove that this works in any case. If you want to know more about that, I would recommend looking up Decoherence. There's a couple of books I really like about it. If you're interested, I'll put them in the description. Some of you might be very confused right now. Like, how is this thing that I just showed you, just a bunch of maths and this little example, many worlds? Isn't the many worlds interpretation about how every time a measurement happens, the world splits into two, and there's like many copies of yourself in different worlds, and all this like extra stuff that sounds really crazy? Well, like, I think that many worlds is just like a bad name for this thing. That stuff does happen, but it isn't fundamental. Instead, it's an emergent property. So let's go back to the example to see why, in fact, it will look like the world split. Let's get rid of everything, and then let's talk about the many worlds point of view. So let's say that I'm going to do a measurement here of whether this electron is up or down. Me. The state of the electron starts off as a superposition of up and down, but the standard interpretations of quantum mechanics would say that when this person measures, then the state has to collapse to one or the other. So perhaps we get rid of this one, and so this person, they're in the state where they have seen the result up. So that's the standard description. But here's how many worlds would see this. Well, collapse never happens. So what happens to this person? Are they going to see one or the other, or are they going to somehow see both? No, what they're going to see is up if the electron is up, and down if the electron is down. So that is the new combined state. If you remember, this is very, very similar to what had happened when instead of this person being here, we had just had that one particle interacting. So what does this mean? Well, you might object that, like, of course this person should be able to tell that they're in a superposition. There's suddenly two of themselves. Like, surely they would notice. Well, they won't. Because how can they notice? Every measurement that they're going to try to do to verify that they and the electron are in a superposition will not work. Remember, when we had done it with this particle instead, so instead of this person being here, we just replaced it with this single particle. After that, whenever you try to do any experiment that would be able to verify that this electron has in fact not collapsed, you weren't able to find any evidence of that. It would look for all intents and purposes like the electron had collapsed. And so this person is just unable to do any experiments. She might try this one. She might try some other ones. She can try anything she wants. She can try to verify that this electron is in a superposition, and therefore there are two versions of herself. But she won't be able to. Every experiment that she does will look for all intents and purposes like the wave function really has collapsed. And this means that she loses access to the version of herself that saw the other result. So there's this version of her that saw the up result, and there's this version of her that saw the down result, and they will not be able to speak again. These two parts of the wave function no longer have any interference between each other. there is absolutely nothing that you can do on this branch to figure out that there is another branch. But because this is all emergent, it is possible to reverse this whole thing. Remember that the Schrödinger equation and all of the normal nice parts of quantum mechanics are time reversible, whereas collapse, real collapse, is not. So it is possible for this person to basically undo everything that happened in that original experiment to put herself back into one person. But to do that, she would have to take all of the atoms in her own body, in her own mind, in the measurement device, every single thing that interacted, and basically put them back to where they were originally. And that is a really difficult task. The more atoms that are involved in the so-called measurement, the harder it is to ever put the two parts of the universe that were twained by that measurement back together. And so that's why, for all intents and purposes, it's like you have two separate worlds. Okay, so that was the many worlds interpretation explained pretty badly and pretty fast. I am on holiday, so I hadn't even planned to make this video, but I've been promising it for 3 years, so I decided to just kind of do it off the cuff. But I'm sure that loads of bits were not explained well, so how about you leave me comments for the bits that you would like to see properly explained, and I can either do a follow-up video or just make this video again entirely. I'll leave links to whatever I end up doing around here somewhere. Thanks.